Hello, my name is Antonio Reed Silva, and I'm going to present a formal verification of the integration of activity and work goal-based workflows. So first of all, I'm going to give you the context, and the context is when you consider knowledge workers in your organization, and you want to allow them to deviate from the standard behavior when they work towards to accomplish a business process. And because of that, usually what you provide business models that are descriptive, such that you trust the knowledge worker on how to accomplish the standard behavior. But on the other hand, the problem with these is that most of the times the organization wants to enforce a standard organizational behavior. And even for knowledge workers, most of the times there is no unexpected situations during the execution of a business process. So most of the times inside the organization, we'd like to enforce this standard organizational behavior. So the idea is, can we have the both of the better of both worlds? And what we have been proposing is the idea that you can have for a business process, you have two descriptions, a prescriptive and a description of the how to accomplish the business process goals, and to provide the ability to switch the execution between the two perspectives. Okay. So I'm going to give you an example. The example is a doctor appointment, and a very simple example where you basically to accomplish a doctor appointment business process, you need to create an episode and an episode instance, and then you have to define the reserve date, attribute, the check-in and the check-out, and you need to associate the episode with a patient, with its attributes defined, and you need to collect data, and then you need to write a report. And so this is a typical UML diagram, and we added a few constraints. The first thing is that episode is mandatory. It means that to accomplish the business process goal, you actually need to define an episode instance and all its attributes. And then, of course, because of these dependencies associated with the multiplicities, you also need to have a patient, the data and the report, but you don't need to say that. You just need to say that this is mandatory and this is inferred. And then you have dependence constraints, and these dependence constraints means, for instance, to check out, so to define the attribute checkout, is necessary that the check-in attribute is already defined and the report description, so that you go this way, the report description is also defined. And then to define the report description, it means that the data, blood pressure, the blood pressure needs to be defined as well. So that's a dependence that goes this way. So basically the idea is that any execution should preserve these dependencies. But of course, as you can imagine, there's a lot of different ways to actually create and to create these entities and define these attributes. And so I'm giving an example of a possible business process, which is a typical one where you basically register the patient, you book an appointment, then you check in, then you collect the data, write a report, and check out. Okay, and each one of these activities actually has a set of pre and post conditions. So to register the patient has no precondition, but has a post condition that you basically create an instance of patient and its name and address. And for the book appointment, what you have is that you need to have a precondition that you need to have a already defined patient, and then you just create the episode and the reserve the date. And also you need to define the multiplicity. So you need to associate these patient with this episode with the respective patient. And so that's the way you define it, okay? Very similar. Just in bold, you can see the cases where you have the dependencies. And you see that in this particular implementation, or in this particular implementation of an activity model associated with that data model, you are actually respecting the dependencies, because here, when you write a report, you need that episode data. Blood pressure is already defined, which is true because this is done in the previous activity. And for the checkout, the same. You need to, the check-in is already defined, which actually is in a previous activity, and the report, episode report description is defined as well, so which is actually in the previous activity. But so with this you can accomplish the business process goal. But if you want actually to have something more flexible, you have a goal model with actually here you can, for instance, you just need to look this one, for instance, book appointment. You can just create an episode and reserve a date without actually associating a patient, or we can associate the patient later. Okay, and even here you can create a report and without having a book appointment. Okay, and of course you can write the medical report there. So here in bold are the preconditions associated with the dependencies as well. As you can see, by executing according to this model, it's more flexible. Okay, but you don't follow, you are not following the standard behavior. Actually, you can check in much later than at the beginning, for instance. Okay. So, how do we achieve these? How do we build these two models? Actually, we just define the data model as we present. We have an automatic generation to a state model that I'm gonna describe later. And from this state model actually is the base where you have automatic generations for the activity model and the goal model. Actually, this state model defines the pre and post conditions that any model or the execution of any model should preserve at the end. Okay. And then you have manual transformations where you can basically manipulate this model and create the particular activity or goal model you want to have. So, what are the problems we are addressing in this paper? So the first one is, do executions according to each one of the models produce the same results? So we want to, if I execute according to the goal model, can I achieve the same goal than if I basically execute according to the activity model? And another thing is that how can we design semantically equivalent models? So how can I guarantee, for instance, in the previous case, that actually this model here is equivalent to that model? So I need to analyze what I do in this automatic generation and what I do in this manual transformation of each one of the models. So the structure we followed in this paper was to use Alloy as a verification tool. So it's a very well-known software for software verification, and so and build small models to prove that the different cases hold, so different situations hold. So what have we done? Actually define a structure where we can reuse our solution for different cases. And on the left side we have the generic part, so you have an alloy generic data model, and then you have the alloy specific data model. So here we define predicates and signatures that are common to all the models, and ones for the specific area. I'm going to show some examples here for for instance for the doctor appointment case. And the same applies for the alloy generic state model and alloy specific state model. And then you have the two models for the goal and activity here. And of course, we define execution models according to the activities and according to the goal and to the activity. These models are important because we are going to simulate the way basically you execute the business process using these model execution. Okay. So the first example is the data model. Here you see the generic part, you define entities, you have attributes. The attributes can have multiplicities, okay, and in inverse attribute, multiplicities and inverse attributes are relevant when actually you are representing the relations between entities, which we here implement specify as attributes. Here we define the dependency, and you see on this side, for instance, for example, the specific model, the example of a patient that is an entity, and then you have two attributes, or the two attributes of the patient name and patient address, that are examples of attribute. And this patient episode is the specific case of an attribute that actually is a relation between two entities. In this case, you need to represent the inverse, which is the one that goes from episode to patient. And this is an example of a dependence where I define that the report, the source attribute, which is the report description, and we see that report episode data, blood pressure. So I'm representing here, or specifying here, that actually to define to define the description of the report, I need to have already defined the blood pressure. Then you have the state model that is the one that is the base for both models, for the activity and the goal model. And the most important entity here is the concept of state. So state is basically a set of entities and a set of attributes. Of course, an attribute, so the entity attribute can be an entity or a value, depending if the attribute is representing a relation between entities or just an attribute of an entity. And we define a particular example of value, which is the defined value. So we are not considering, because it's not relevant for what we are doing, considering the specific values. What is relevant here is just to say whether the value is defined or not. And then we define in the state model a set of predicates. I'm only representing here one of them, which is the dependence, that says that this predicate verifies if in a particular state a particular dependence holds. Okay, so it will be true if it holds. And actually, I'm not representing here, but there are a couple more of predicates for the generic state model. Okay, and then we have a specific one, okay, that is the final state. So this predicate is final and defines one state where this holds. And here I'm reusing already the predicates I defined in the generic part. In this case, I'm just illustrating with the dependence, but all the others for the multiplicity, that the relations are bidirectional, that the attributes are defined, that the entities are defined. All these this is the final state of our represents the final state of our doctor appointment case. Good. And another thing that we are going to represent that is specific to our case is a set of invariants, because another thing that we want to show is that during the process of executing the business process, there are a set of invariants that should hold. For instance, since our approach is that the way you build you execute the business process is monotonic, so you just increment the number of entities that you create, and you keep defining new attributes. So, for instance, you say that there's no multiplicity exceeded. So that's in the sense that actually in a particular intermediate state, for instance, if one entity is connected with at least 2 or 3 other entities, you can, and in some intermediate state, you can connect it to 1, but you cannot be connected with 4, because that would exceed. So you have these invariants. So with these, we are going to show that we achieve our that both models achieve the same results. So we define this final state, and you define these consistent states. And you are going to simulate the execution of the business process such that try to see if we achieve this and that these consistent states are never. So that intermediate states never violate the set of invariants. Okay. So to do that, we need to define what is our activity model. And so an activity actually is an entity where you define a set of entities, a set of attributes, and a set of relations between entities. Okay? And for instance, in this case, so this is the generic part. The specific part, you say that book appointment, you define an episode, you define for this episode, you define the reserve date attribute, and you need to pick one patient that already exists in the state, and you define the relation between the episode and the patient. And now you have the execution. So this the generic execution, this is reusable for any execution, and now I'm just showing it for the activity, but you have a similar definition for the goal. And so in the initial state, basically you have no entities and no attributes. And then you define a set of traces, and the traces are the sequence where you apply the execution in a state by executing an activity A that results in state S prime. Okay? And so these will generate all the states, and the alloy will generate all the states, and we're going to verify that all the states preserve the invariance, and that we can achieve one state that actually where the final state holds. Okay. So this is an example of the execution. So this is the generic code for the execution of an activity, and we'll see, for instance, this is all the things that should be preserved. So if in an activity I define entities, the entities to be defined are not defined yet. For this is verified there. And then I have a change state, and in the change state, which occurs at the end, we just, as a result of executing the activity, I change the state, and I create actually I say which entities are in S prime and which attributes are defined in S prime. Okay. So, and then the specific part, what we just do is just we run to see if we can achieve the final state, and we check if this assert is preserved, so if the invariants are preserved. For example, in this case, what we check is for all states S and S prime, such that the execution of S and activities, when the result S prime is the result of executing activity A in state S, and if the invariants hold in state S, means that the event should hold in state S prime. And I'm going to just give you just a demo of this. So I have this, I'm going to execute the first one here, and the idea when I execute, the alloy is going to provide me, if I can achieve, it's going to provide me a final state, an instance where that verifies the condition. So it was successful, so, and I have these we were able to generate this instance of the business process that actually accomplishes the goal of the business process. In this case, using the activity model. So we are using the activity model there. To verify that the intermediate states are consistent, I just run this one, and in this case, alloy is trying to find a counterexample. Okay, and it finds a counterexample means that there is a particular sequence of execution of the business process where one of the intermediate states do not preserve the invariance, and it was not able to find a counterexample. So that is the way we use alloy in this case. And just to finish, We also, what we have done also is to show that both models, the activity model and the goal model, are equivalent, and we use induction. Basically, you have done induction in the construction of by induction in the construction of a business process. Okay, by the execution of a business process, and in this case by the construction of a data instance model. Okay, a data instance model, which we see that by applying these operations, we also achieve the same. We can achieve the same result in the construction of the data model. Okay. So conclusions. So we were able to formalize a basic model for the design of activity and goal models, which are based on a data model and provide different execution perspectives for the same business process specification. And the use of Alloy specification language has shown to be useful in the definition of the semantics because it accomplishes two different goals. One, a specification that can be immediately verified through the generation of small test cases, and the use of an induction approach to prove the consistency of the models. So finally, as final work, we want to apply the same approach to show that by switching between the two models, we can still achieve the final goal of the business process, and that the intermediate states preserve the invariance. Okay, thank you.